When we are working in the coordinate plane, there are two common equation types. There are what we call explicit equations, and an example of an explicit equation might be something like, for example, y is equal to x squared, something really basic like that. So y is equal to x squared. Now, in a situation like this, it's very clear to us what the relationship is between y and x. We can see that y can be explicitly defined in terms of x. Y is whatever x is squared. Or if I said something like y is equal to x plus 1, for example, y again is explicitly defined in terms of x. I can also write this as x is equal to y minus 1. In this case now, x is explicitly defined or expressed in terms of the other. So this is what we call an explicit equation. And this is primarily the type of equation that we have worked with thus far in our math careers. There is also something called implicit equations. And this is a situation where the relation between x and y, between x and y is implied. And a classic example of an implicit equation might be something like x squared plus y squared is equal to 1. Now, this is not to say that you can't express y in terms of x or x in terms of y, because a lot of times, most implicit equations, you might be able to do that. But I do want to highlight here is that this is a situation where their relationship is implicitly defined. That is to say, there clearly is some type of relationship between x and y. We're just not entirely sure what that is at this time, just because of the way it's currently expressed. So another example might be something like xy plus y squared is equal to 3, right? Where it may be a little tricky to try to express y exclusively in terms of x or x exclusively in terms of y. And there is, again, some type of relationship between the two, but it's implicitly defined here. So what we want to cover in this lesson is how to differentiate implicit equations. How do we differentiate an equation when the relationship between x and y is implicit? And now that we've covered the chain rule, we can do this pretty efficiently. So let me just go ahead and jump to kind of a blank page here and let's consider that first example I gave. So x squared plus y squared is equal to 1. So I'm going to go ahead and do the implicit differentiation for this. I'm going to break down the process, but hopefully in doing so, hopefully try to illustrate why this is effectively just the chain rule in action. So let's consider this example. The first thing I'm going to do is I'm going to go ahead and I'm going to differentiate both sides of the equation. So d dx of this entire equation. So I'm going to write that. I'm going to differentiate both sides of the equation with respect to x. I'm going to differentiate both sides with respect to x. Now let's take a look real quick at what this means. So if I go ahead and differentiate the left side now, I'm thinking, let me just set up first each part. I'm differentiating x squared, okay? And then I'm going to be differentiating y squared, so let's write that. So we got d dy, or d dx, excuse me. And now I'm going to differentiate the right side, so I'm differentiating 1. So let me go ahead and write all that out. Okay, so let's break down what we just did. So first off, let me do this in purple, for example. What is the derivative of x squared with respect to x? So if we just differentiate using the power rule, we can say that this is just simply 2x. Now, let's do this next part let's try green. Let's differentiate y squared with respect to x. We're differentiating y squared with respect to x. Now, in doing so, we'll notice that we don't have a function in terms of x right now. We've got the function y. So we're going to have to apply the chain rule here. We're saying we're differentiating y squared with respect to x, y squared with respect to x, times the derivative of y now with respect to x. Now pause and think about this for a second. Oh, sorry, I apologize. This was the derivative of y squared with respect to y. Let's pause and think about this now in the context of the chain rule. What we're effectively doing is we're differentiating some function. Y squared is some function. Now, what is this function in terms of x? we don't really quite know. So all we can do is differentiate the outside. So to say the derivative of y squared with respect to y, and then the derivative of y now, so the derivative of y with respect to x. This is exactly what we did in our previous lesson in regards to the chain rule. We're differentiating the outside, then differentiating our inner function with respect to x. So once we understand that, we can see that what we have here, if I kind of break this down, we can say the derivative of y squared with respect to y is 2y. Now, do we know what the relationship is between y and x? And the answer is no. So when we differentiate y with respect to x, all we can really do is write this as dy dx. This is sort of like a placeholder. We don't quite know what dy dx is, so we're going to leave it as it is. And in fact, the whole point of implicit differentiation is to try to find out what this dy dx is. So just to recap this process here, we're differentiating y of x, or y squared, with respect to y of x, and we're multiplying it by the derivative of y of x with respect to x. Okay, that's just the chain rule. And just to finish this off, we've got now the derivative of any constant, which we know is equal to 0. Okay, so let me just write out clearly what we just have. We said the derivative of x squared with respect to x is 2x. The derivative of y squared with respect to x is 2y times dy dx. And the derivative of any constant is equal to 0. Now, our goal from here is to try to solve for, I'll write this on the side, we're going to now to try to solve for dy dx. We're going to solve for dy dx. Now, at this point, I want to emphasize, now that we've kind of broken down what dy dx represents, it's the derivative of y with respect to x, you could also use this as y prime from here on out. And you'll often see me use y prime. I'm going to continue working with dy dx for the rest of this problem, but if you ever see me using y prime, that's what I'm referring to. And that's totally fine. So we're going to solve for dy dx now. So just using basic algebra, we're going to say 2y times dy dx is equal to negative 2x. If I move that 2x to that side. And then dy dx is equal to negative 2x over 2y. And if we simplify this, we can divide out the 2's, and now we can say dy dx is equal to negative x over y. So what is the derivative of y with respect to x? It is a function that tells us the slope of the tangent line on any given point of our graph of our function. And what type of graph do we have here? Look back at our original equation. And you guessed it, it's a circle. So if you're like me and you're a visual learner, you may want to see this here. Hopefully this will help. What I went ahead and did is I graphed that circle. It's just a circle with a radius of 1. So let me just label this as 1 and 1 here. And suppose, for example, I wanted to find a derivative of dy dx when theta is equal to pi over 4, when my angle is pi over 4. Well, when my angle is pi over 4, what are my x and y coordinates? Well, root 2 over 2 and root 2 over 2. So what is the derivative now at the point xy is root 2 over 2, root 2 over 2? Well, I'm going to plug those in. So negative root 2 over 2 over positive root 2 over 2. And all of this gives me just negative 1. And what is that? That tells me that the slope of the tangent line at the point root 2 over 2, root 2 over 2 is indeed negative 1. So the derivative here of this implicit equation gives me a function that can determine the slope of the tangent line, or the rate of change, at any given point of our circle. So really, if you take a step back and look at it, in practice, it's pretty straightforward. We're just going to be differentiating both sides of the equation, remembering that when we're differentiating with respect to x, since we don't quite know the explicit relationship between y and x, using the chain rule, we're going to have a placeholder of dy dx, which effectively is what we need to solve for when we are doing the implicit differentiation. So let me go ahead and let's try just another problem together just to make sure that we really have this down. If you want to pause the video right now, I went ahead and I wrote down the steps for implicit differentiation right over there. But With that said, let's just go ahead and try just a couple of problems just to make sure that we really have this. Let's go ahead and try something like number 3. Zoom in on that. So we're going to differentiate both sides. So we're going to say the derivative of all of this, x plus y squared, is equal to 2x. So the derivative of the left side of the equation, using the chain rule, we're going to say 2 times x plus y. And then we have to multiply it by the derivative of the inside of our function, or the inner function, if you will. So differentiating x plus y is 1 plus dy dx, or y prime. So the derivative of y with respect to x, we can just write it as dy dx, or y prime. And then this is equal to the derivative of the right side, which is just 2. And again, our goal is to try to isolate that y prime. We need to get this by itself. So we're just going to use some inverse operations here. So 1 plus y prime is equal to 2 over 2 times x plus y, which we can actually simplify. That should just be 1 and 1. And then y prime is 1 over x plus y minus 1. There's our derivative, okay? And this is of our equation here. Let's go ahead and try one more. Let's do one with a trig function in there. Let's try something like number 6 here. Well, for number 6, again, we're going to differentiate both sides. So let me just kind of write this here. We're going to differentiate both sides here. So the derivative of cosine y is just negative sine y. The derivative of 1 is just a constant. Oh, and you know what? I forgot something. I'm moving too fast here. The derivative of cosine y is negative sine y, but since our argument is y, I've got to apply the chain rule. What is the derivative of y with respect to x? Well, that's y prime. Okay, so that was the chain rule. Derivative of the outside times the derivative of the inside. Now, I'm going to continue on. The derivative of 1, we said, is 0. The derivative of negative x is negative 1. And the derivative of the right side is 0. So negative sine y times y prime is equal to 1. Y prime is equal to negative 1 over sine y. And we can rewrite this as y prime as being negative cosecant of y. Okay? Either one of these work just fine. So I'll just box both. Okay? So hopefully that gives you a good understanding of why implicit differentiation works and what exactly it means when we say we are doing implicit differentiation. So I encourage you to try the rest of these practice problems now on your own and check your solutions with what I have uploaded to our website.